welcome back to Daily Leetcode. Today we'll be solving candy. In this problem, you're given n children standing in a line. Each of them is assigned a rating based on a ratings array that they give you. And you have to follow these two constraints. Every child must have at least a single candy, and any children with a higher rating should get more candies than its neighbors. In the end, you want to return the minimum number of candies you need to distribute so that these requirements are all fulfilled. So if you look at the first example, you see that here this child has a rating of 1, whereas this one has a rating of 0. So this one should have more than its neighbors because it's greater. So in this case, you can assign this, 2 candies because you need this one to be at least 1. You can't have it being 0. So if you just assign this to 1 and then this to 2, just like this array, in the end, this is the minimum amount of candies you need to distribute, which sums up to 5. In this case, you can see that you can assign this one a 1. For this one, it has to be greater than this one, so this should be a 2. And for this last character, technically this one is not greater than this, it's just equal to. So therefore, you can actually assign this one a 1, just like this, and the sum is 4. All right, here's another example. We see that for this example, let's just say all the children start at candy of 1 because they all need at least 1 candy. Then we realize, hey, 4 is greater than this neighbor, so it has to have more. So let's just increment that to 2. We know that for this 3, yes, it's smaller than 4, but it has to be greater than this 2. Meaning that if this was 1, then that means this one would have to be 0. And of course, you can't have this. So how do we fix this problem? Well, we just want to increment all of these that add an error by 1. So now this becomes 2, and now this becomes 3. And just like that, we've completed the actual solution. In this case, you would just return the sum of them, which is around 7. Okay, so now this sort of leads to the intuition behind the real solution. So you can see here that what we basically did was we had a traversal forwards, and then to fix all of these errors, all we did was we sort of just traversed backwards, and I'll sort of explain what these two do. Okay, so this problem is basically split up into 2 traversals. One is the forward traversal, and what the forward traversal does is it ensures the requirement for the larger rating satisfying the condition with respect to the left element. We know that it has to respect both the left and the right element, and the right element is what the reverse traversal is for. So let's run through this example again. So in this case, remember that they're all initialized to 1. Let's write it here. And now we see that this one's larger, so we're going to make it a 2. This one's smaller, so we don't care. This one's smaller, don't care. So you can see that, yes, for this 4, it is true that it has a better rating than its left neighbor. That's what the front traversal does. And now that we go backwards, we see that, hey, this is going to satisfy, ensuring now it satisfies the right neighbor. So in this case, we see that 3 is greater than 2, so therefore this one should now increase. This one is greater than that one, now this should increase by 1. One last special case to realize is that, let's say we have something like this. We initialize all of them to 1. In our forward traversal, this would become 2, and this one would become 3, and this would stay the same. In our backwards traversal, we realize that 7 is greater than 4, so you might think, why don't we just increment it then? Well, you actually don't have to, right? Because 3 is already much greater than 1, so there's no point in actually incrementing because you're trying to minimize the overall sum in the end. So we only want to increment if this number is, let's say, if it was 1, then we would want to increment. Otherwise, if it's already greater, there's no need. So that's the one special case. Other than that, that's the entire drawing explanation. And yeah, let's hop into the code. All right, so let's start off by creating our array of candies, which is basically just going to store all of the candies we give to the ith person. In this case, we're just going to initialize all of the children to have 1 candy because we know that's one of the requirements. So now let's go with our forward traversal. So I'm going to loop through the entire array -1 because I want to compare. So I'm going to say if ratings at I plus 1 is greater than ratings at I, that means this one's greater, so it should have a greater candy count. So I'm going to say candies at I plus 1 should be 1 more than the former. Now we can do our backwards traversal. So I'm just gonna do it in like the same manner. In this case, I'm gonna start at the end of the array, and rather than going to the very end, I'm just gonna stop one before the very end. And now I'm gonna say if ratings at I minus 1 is greater than ratings at I, that means this one should have a higher candy count. So it's very similar. We'll do the same thing. The only exception is, recall the special case where if this candy count was like 4 and this one was like 2, well, there's no need to make it even greater. You don't have to add it by 1 anymore. So instead, what you want to do is you want to ensure that you do have to add it. So candies at I minus 1 should be less than or equal to candies at I. Because if it's already greater than, there's no point in making it one more. It's already satisfying that requirement. So you only want to do this if this is strictly less than or equal to. And yeah, that's basically it. You basically constructed your candies array with the minimum amount of candies which satisfy both these requirements. So in the end, you can just return the sum of candies. And yeah, I assume it should work again. And yeah, I hope you guys enjoyed this video. And yeah, I'll see you guys.